And he's going to be talking about easy AI in Python.
Hello, everybody. Ready to have some fun? All right, we've got some themes today. It's some of these concepts for everybody here who's a little bit computer sciencey, pretty good programmer. Some of these things will seem easy to you. My goal today is to parade past you a whole range of AI-type topics that can be done very easily in Python, that have short blocks of code, and that are, my primary purpose is to show you things that are appropriate for teaching other people Python, especially teaching your kids, teaching high school students. My feeling in the past is that we've taught kids with programming problems that are boring. They solve the problem, they write a hangman game, they know how to generate an HTML page, and they kind of get the gist. You teach them to do some AI with Python and teach it in a way that is small enough to where they can wrap their hands around with it and experiment with it. I think they'll be in this room 20 years from now giving a talk. So I'm going to parade these things past you kind of fast. Along the way, I'm going to give you a tour of some newer features in Python that make these tools easier to experiment. So we're going to cover code fragments because one of the themes is that there are small code fragments, but we don't have enough time to actually sit there and analyze each piece of code. So some of the code blocks will fly up on the screen and go past really quickly, but I will stop on each page and give you a link to the code. All of the code is on the ASP.NET cookbook, and so it's easy to find. You can go to the cookbook and look for my name, or you can write down these recipe numbers as we go. So, themes again. These are easy to use tools, easy programming exercises. They're short. A particularly interesting part is their general purpose, meaning that you can ignore the problem domain that I'm giving you, the puzzle problem, and replace it with real problem domains. Instead of solving a puzzle, solve a business problem. And the same framework should work for large problems as well as small problems. And I hope all of you go show a friend or someone something they can do in AI, in Python, easily and quick, and be astonished. Myself, I've been astonished as I put this together that something as sophisticated as a neural network could be put together in about 30 lines of Python. I thought I would write a program that played Mastermind, and it took a few lines to display the Mastermind, write the comparison function, but to actually have the AI program solve the Mastermind only took another handful of lines. It was one screen full of code. I thought, Python rocks. So let's go. Here are the topics. Are there any bets right now on whether I can fit this into 45 minutes? Okay. There are three new editor tools in Python 2.6, permutations, commutations, combinations, and product. I'm going to show those off because they take a certain class of AI problems, the exhaustive search problems, and make them really easy to code. And it takes it out of the range of problems that you would give to a university student and makes them problems that you can give to a student in junior high. So we'll do a couple quickies there. Some real meat here is in the next section on neural nets. And I say it's real meat in that most of the other things, like I would bet 95% of this people in this room could easily write their own breadth-first recursive solver for a puzzle. But I'll bet very few people in here have an idea of how to put together a neural net in a handful of lines that's useful for studying databases. So that'll be one that we spend a little bit more time with. Number 4 is particularly interesting. It is a generic puzzle-solving framework. It is about a dozen lines of solving code for puzzles, and the interesting part is not the puzzle solver, but when you're giving this to students, you come up with you give them new puzzles, see if they can come up with a representation for it, a goal state, how to generate the next move, and an initial state, plug it into the solver, and it generates the solution for them. The fun part is not the solver itself, it's giving them new puzzles and seeing how quickly they will adapt it. So for number 4, we'll look at several different puzzles that can be solved with that one framework. We'll do constraint propagation and probing search strategies. A lot of AI. I have 41 minutes left. Let the games begin. 8 queens, 6 lines. The 8 queens problem is a traditional programming problem. Lots of computer science people have played around with it. The challenge is using recursive procedures. Another part of the challenge is backtracking. Lots of things that you would hand to a first-year university student to teach them about how to solve the puzzle. IterTools now provides a permutations generator. So it can loop over all of the columns and give you all permutations of the columns, where to place the queen on each of the 8 columns. So the part that was very computer science-y, the part that challenged your first-year computer science student, has all been encapsulated for you in the permutations function, and the student can get to the part that for them is fun, which is the second part. This is a part that the student can write easily, and each of those two, that if statement, is something that in a 1-hour class with a junior high student, you can teach them why this works. And what this does is essentially compute any 2 queens on the same diagonal. Not a lot of meat to that code. There's a lot of different ways to write this and to compute whether or not 2 queens are on the same diagonal. My important point for you is that IterTools permutation is a great way to start doing AI problems with brute force searches. Generate all possible permutations. Check to see if one of the permutations matches the solution that you want. Notice that I do a print when I find a solution, but I don't do a break. What that tells us is it doesn't stop at the first solution. It generates all possible solutions. It's a fine thing. It runs in a couple seconds. It's fun. 8 queens, 6 lines. Alphametics. Who's ever heard the term alphametics? Okay. I had never heard the term before, but I had seen the puzzles since I was a little kid. Who has seen puzzles of this variety before? Okay. So I won't spend much time explaining them. Generally, the idea is that the problem is you are given a cryptogram, sin plus more plus money. You have to substitute in the letters 0 through 9 for the digits to make the equation true. The non-obvious part of the constraint is that leading digits like the M and the S are not allowed to be 0 because that's not the way we normally write the numbers. Phrased another way, we would like to look at all permutations of digits and their mappings to the set of letters in this problem. Once we have a mapping of S to 9, E to 5, we then need to apply the mapping, which is very easily. We use the string translate function. And once we've translated it, we've produced an equation like this. How do we check to make sure the equation is true? Eval. A lot of you have been taught to hate eval. Don't hate eval. Love eval. It's a security risk. I wouldn't expose it on the net, but it's great for problems like this. Here's a bunch of standard problems. It's on the ASP.NET recipe, so you can see I love some of these. Abra plus Cadabra plus Abra plus Cadabra equal Houdini. What was the cute one? North divided by south equal east divided by west. Where's the one with the zeros? There was one that said something. Not squared equal 0 cubed. Go figure. The thing to take away from this slide is that in contrast to other approaches to solving this problem, just brute forcing it allows you to solve a huge range of problems, such as multiple variables, using squares and cubes, using differences. Any other mathematical magic in here? If sines and cosines produced usable results for this, you could use them here too. The point is, anything that you could stick into a val can be run through this equation. We just drop the digits in for the letters, eval it, see if it's true. Easy peasy. Code. The hard part of the code to write for a beginner, and the part that we just give them if we're teaching this, is we give them the first part that shows how to break the words apart, compute the set of letters. And so once we have the list of letters, so give them this part. Here's the meat, the part to teach. Loop over all permutations of digits. With those permutations of digits, check to see if 0 is one of the leading digits. If not, skip it, because remember, we don't want to start send with a 0. That piece of logic was encapsulated in one line, is 0 at the beginning. Once we have the permutation, let's substitute it in. Easy enough. We make a translation table using string make trans. Apply the translation using the translate built in. which gives us an equation with the digits dropped in. How do you tell if the equation is true? Run it through a val. If a val returns true, then we have a solution. Once again, there's no break at the bottom. There's just a print. That tells us that it doesn't just stop at the first solution. If your arithmetic has more than one solution, it'll print all possible solutions. How long does it take? It's not instant. You know, it has to run through 10 factorial of permutations, but it doesn't take long either. All of these were solved in, I think, just a few minutes on my machine. I just looped over them one by one, dropped it into the solver, answers pop out. I think students will find this fun. I think they will find this logic to be transparent. It shows off itertools. You can teach a 7th grader how to solve the arithmetics, and you have empowered them in a way that other people who've learned to write hangman programs are not empowered. Got my gist? Go teach Python to people and hook them with AI applications. So we've done brute force. Who's here is excited by brute force solution? Okay. Brute force doesn't sound very AI-like. I mean, we weren't that impressed with Deep Blue when it defeated Kasparov using brute force. So let's go to something more interesting. What we really wanted out of AI was not for Deep Blue to use brute force, but we wanted it to think. Think like us. We wanted to model the human brain. Here's the recipe number in the cookbook for those of you who want to follow along. Take a look at the source code. Once again, if you don't write them down, you can just go to the cookbook, put in my name, and all these recipes will pop right up. This is a classic example of neural nets. It is taken from the PDP book. I think it stands for Parallel Distributed Processing, which was a very popular book when I was in the beginning of high school. In other words, very recent. And the example of the model is called IAC, Interactive Competition. So here's the mind-blowing comparison. A database is a model of a brain. Every field's a neuron. Neurons are connected to each other, and so any fields that are on the same row in the table excite one another. Anything in the same column that has a different value inhibit one another. So you have some neurons exciting, some neurons inhibiting. If we go through many iterations of this, we can touch something and excite it, see what other things it excites, what those things inhibit and excite, run many iterations until the brain reaches a stable state, and watch this percolate through the brain and see what it tells us about our database. It's kind of cool. Who here has ever studied a database or mined a database using this technique? Wow. Okay. I'm going to teach you something new and special, something that you can use. Let's don't teach this to the kids. Let's keep it for ourselves. Okay, how do you use it? Do you remember the old experiments where they cut open a person's head? Okay, let's say a frog. They inserted an electrode. They excited part of... I'm going to go back to a person, because when I first read about this, I read that they opened up the head of a person who was still awake, and they would probe, and they touch it, and it would excite, and it would bring back a certain memory. What they did is excited a part, it percolated throughout the brain, generated a certain thought. We're going to do the same thing, but to our database, and we will use no anesthesia. Okay, provide a stimulus, see what gets activated. Would you like a picture? Stimulus. The blue things are the parts that are activated. This seems like a simplistic slide. I hope you can memorize it, though, because it will explain what we're about to do. Put a stimulus at some part of the brain being your database. See what lights up. There's the model of neurons, axons, and synapses. What can this approach do that SQL can't? Because SQL is what we traditionally use to mine our databases. It can do cool things. It can generalize. SQL doesn't do so well when there are missing records or missing data. And SQL can only tell you about the data that's in your database, not the data that's missing. Would you guys like to see it in action? This is the example given in the PDP book. It's famous. The Jets and Sharks example taken from, what was the movie? West Side Story, right. Best Picture, 1968, I believe. Okay, Jets and Sharks. There's the name of all the gang members. There's actually about 30 of them. I put the ... in the middle just to shorten the list. We know which gang they're in, either they're Jet or a Shark. We know approximate age group, 20 years old, 30 years old, 40 years old. Level of education, they go junior high, college, high school. I believe this was a marital status, single, married. These are not my abbreviations. These are the ones used in the real example. And how these guys, their avocation, pusher, burglar, bookie. So we're going to study this database using a neural net. Remember, this isn't a database, actually. It's a brain. Okay, so there is a neuron for every unique value in the database. So Art gets his own neuron, so does Al. That kind of corresponds to records. But this part's unique. 20 years old gets a neuron too. So it is in the field of age, we take all of the unique values, 20, 30, and 40, and each one of them gets a neuron. All neurons start at a resting state. The way they get excited is if they're on the same table row, if you light up one, anything that's connected to it gets lit up too. Inhibition, things in the same column inhibit one another. So, well, that kind of makes sense because we excite the 20-year-olds. We'd like to inhibit the 30-year-olds and 40-year-olds. So this is the competition part of the IAC interactive competition model. Light this up. These two guys should get inhibited. Whoever is 20 years old should get excited. Not terribly interesting on the first round. More interesting, we light this up. It turns out Al, who's 20, gets lit up. Attributes associated with Al, like him being a shark, get lit up. Being a shark lights up some 40-year-old and a 20-year-old, but inhibits the 30-year-olds. Then it starts to percolate all the way through. It's the multiple iterations of this that lead to the analysis of the database. Okay. The command to stick a probe in the brain is touch. We're going to touch the kin element and give him a jolt of electricity equal to 0.8 units. Zap! Let the calculations run, and we get a printout of all the neurons of how much they are lit up. Do you remember the little picture of the brain? We touched kin, that's the red star. The blue stars, the part that light up, are what come out. So this is a level of energization of each of the other neurons. And what we see when we touch kin is that sharks light up quite a bit and jets are negative, which kind of makes sense. SQL could have told you that kin was a shark. And also we saw that being single lit up quite a bit. So that is a characteristic of kin. There are some these other entries for other people are lit up too, and they give you measures of similarity. Kin's lit up the most, which we kind of expect because we applied the juice there. But look how much Nick is lit up. He's got 0.3. That 0.23. That tells us that Nick and Neil, who also has 0.3, are more similar to kin than any of these other characters. You're like, and so if you would ask the sharks and jets, they'd say, oh yeah, Ken really hangs out with Neil and Nick a lot. They're a lot alike. That's what this told you. That's something that you can't get from a SQL query of the same database. So who's alike, which characteristics mostly match? That was generalization. Generalization from a specific instance. You can also generalize from multiple instances. Pick several people and say, let's generalize this group. Something else hard to do with SQL. Is anybody excited yet? Somebody thinks this totally rocks? All right. Query the neural net for a given set of facts. Crime scene analysis. I don't know the name of any CSI character, so I will make one up. Rachel, the chief crime scene investigator. What facts have you ascertained? Well, we know the person is 20. They're a shark. They went to junior high. They're singular, and they're a burglar. Yes. Well, what's their name? We don't really know. So we query our database. We touch all of those neurons, and we see what lights up. Out of the individuals, the ones that light up the most are kin is the best match, and then we have several that match to the same degree of Lance, John, and Jim, and then the rest of them are not matches at all. So we've narrowed down our list of suspects. So, got a set of facts. You can query your database to see how well they match. Something else SQL can't do. Data is missing. The easiest way for me to simulate that in a brain is we've got two neurons that are connected, and I cut the connection between them. Just reach in with my scalpel. Our version here is we're going to light up Lance, but we will disconnect the synaptic connection between Lance and a burglar. That is essentially the same as deleting from the database the fact that Lance is a burglar and marking those entries in the database as blank. So we've taken that relationship out of the database. Let's see what happens, though, when we've touched Lance. We run it through. Lance, of course, because we've touched it, has lit up quite a bit. And we can see Al is kind of related to Lance, but we look down here and burglar lights up quite a bit. That's kind of interesting. The Lance burglar pair was not in the database. How did this light up? The answer is Lance is very much like these other guys, John, Jim, and George, who are probably burglars. Lance is a jet. Most of the jets are burglars. Lance is 20. Most of the 20-year-olds are burglars. It symbols all of the facts. It takes what it knows, and it builds what we would do, form an abstraction, a mental conceptual picture of what this kind of person, what we know about other people, and then compensate for data that's missing. That's pretty cool. Try that with SQL. Do you guys love this? Cool. How much code would a monstrous intellectual giant like this take? The neuron class. We're not going to spend a lot of time on this code. Most of the beginning part is fairly simple. We tell each neuron what pool it's in. Like if the neuron is 20 years old, we tell it is in the pool of 20, 30, and 40. It's in the age group pool. And then this is the instance of the pool class, which has the computations that updates the sum for the pool. And then the engine, the code that runs it, is fairly simple. It updates the sum in each pool. It computes the new activation. After each one iteration where it's computed the activation of each adjacent neuron, it then commits, SQL-like. It says, all right, I've now activated all these. Let's save their new activations. We've activated Lance. Now everything Lance is activated will light up also, and we'll do another iteration. And I typically run through 100 cycles, which is enough to make most of my queries stabilize. And then it just prints the result. That is 100% of the code for this neural net. Pretty cool. Total of 100 lines of Python. It models any database as a neural net. What it does, you probe the brain, it reveals or confirms hidden relationships. You guys love it? Check out this recipe. Show it to your friends. Okay, now out of the realm of rocket science and back into the things that mere mortals can do, but we're going to teach kids to do. So, typically, the computer problem for teaching a kid to write a program to play Mastermind is it generates a random code. The kid has to guess the code, and then it tells them how closely they got. It's almost like being given a test. That kind of bites. But the whole purpose of the computer was to solve problems for us. How about I make up the random code and the computer gets to guess? That would be better. Computers actually solving problems rather than giving you more problems. When I was a kid, the problems I was given were write a thing where you do the guessing. Let's do it the other way around. So, who here is unfamiliar with Mastermind? Okay, very few, so I'll go through this quickly. The code maker picks a random 4-digit code. Here's the important part. He doesn't tell you what it is. The code breaker guesses. He had to guess because the code breaker didn't tell him what it was. So, if this is a hidden code, a tuple of 4 digits, the guess, 4 digits, the scoring of the guess, 1, 2, says that the 3, one of those 4 entries was in the correct position, and that there were 2 of them the other 3 and the 4 that were in incorrect positions. So you're told the number of positions that match and the number that are incorrect. You make successive guesses and you try and home in on the result. There are many possible strategies to use for code breaking. One way to evaluate the strategies is how many guesses does it take? Let the games begin. Interesting part is how experimenting with different strategies and seeing which ones work the best. Something that's actually hard to do when you're playing the game itself. You try one strategy in one game and one on another, but it's hard to generalize what did best. So, it takes about 30 lines to write the whole thing. We're not going to spend a lot of time on this, but you bring in random, obviously, to generate the random code. The part that's hard for a kid to write is the comparison function, the part that does the scoring. I would give this part to them. It's easy for all of you guys to write. It just takes a few moments to think out what does it mean to evaluate, to loop over the 2 tuples, compute the parts that match and parts that don't match. For us, that's easy code to write, but I wouldn't give it to the kids because it gives them a headache. Let's give them the comparison function. Let's go to the fun part, run the game. Oh, by the way, this slide and the last slide was 100% of the code except for the part that has the strategy for making a guess. The strategy for making a guess has got to be an enormously sophisticated module, a function of enormous... Oh, there it is. Amongst the remaining possibilities, the most basic strategy is, I'll pick one randomly. My guess being an actual real guess. So, running it is, you input a hidden code, you say run the game to solve the hidden code. The second parameter here is interesting. I dropped this in as a function. I didn't hardwire it. I took the strategy of random guessing, and I dropped it in as a parameter. What does that mean? It means that I can try other strategies very easily. So far we have seen on these slides this one, and this one. It's 100% of the code necessary to generate the hidden code and solve it, and have a strategy for solving it. So let me go into the steps in some detail. Inputs, 4 digits, the output format string, generate the search space, which is all possible tuples. This code is now simplified a little bit with IterTools product. That code creates a list of all possible guesses, 000 to 999. Scoring function, that's the part I would give the kids. The scoring function takes a guess versus the actual and gives the result back. You have 1 direct hit and 2 in the wrong place. The strategy for choosing the next move, remember that complex strategy? Make a random choice of the remaining possibilities. Okay, the engine to run the game is generate the entire search space, use that strategy, pick one of them at random, score the result, see how that random guess did. Now, given the score of the result, check out of all the possibilities and see which one of those matched the score. Let's eliminate all of the things that score precluded. Something really easy for the computer to do. Let's run it. Here's the hidden code, run game, and here's what it prints out. Starts out with 10,000 possibilities, makes a random guess. It gets none in the right place and 1 in the wrong place. So that reduces it to 3,000 possibilities. Not bad for a first guess. So out of those possibilities, it randomly chooses this one, which once again misses 1 slot, leaving 800 possibilities. Guess, guess, guess. It pairs down really fast. It's down to 50% probability and guesses correctly. And says, hey, I won in 7 tries. Not bad for random guessing out of remaining possibilities. I was astonished that that random strategy, which doesn't involve much of what we would consider AI thinking, is so darn effective for this game. It does pretty damn well. I think out of 10,000, its average number of moves is something like 6.2 if you run the simulation over and over and over again. Easy peasy. You can teach this in a 1-hour class on Python to kids and make something that doesn't put the problem on them. It teaches them to solve, use the computer to solve problems, sophisticated problems, problems that would challenge most adults. Okay. Next issue is making it fast, because some of you might want to say, well, probably you guys would do this. Your kids would do this. Your kids would say, oh, what if it's not 10 possible colors? What if it's 100? And what if the length of the tuple was 1,000? That exhaustive search strategy doesn't work as well. Psycho gives you a 10-to-1 speed up. You can also speed up the compare function in C, and you can also pick better strategies. So what's the fun part? We've basically given the kids the result. The fun part is there are different strategies. We can try them all out. Let's try a new strategy. It says, I'll pick out of the possibilities, I'll pick one of the possibilities that has no duplicates. So I'm not going to guess 1, 1, 1, 1 because that doesn't provide me very much information. So this is the same as before. I pick random possibles, and then I see if all of the digits are unique. If they are, I return that as my guess. It takes 5 minutes to write that. Easy peasy Python. And more advanced strategy. Claude Shannon's information theory tells us the information theoretical content of each guess. So I could go evaluate several possible guesses, apply his formula, the probability times the log of the probability base 2. Be familiar to about a quarter of you in here. For the other 3/4, trust me, that's his formula. And it tells you, out of the possible guesses that you have, which one is the most informative. The more intuitive version of it is every guess breaks down the search space into several different possibilities. It's nice to divide the search space as evenly as possible so that you get the most information from the result. It turns out that in the size of the game I just gave you, that takes the number of solutions down to about 5.3. It's pretty darn impressive. It plays, and it shows you close to the theoretical limit of best possible mastermind play. The very best possible mastermind play is to do this in multiple stages. Say, not only what information does this play give me, but also all the successive plays after that. So it works its way down a tree. It's a little bit harder to program, but not much harder to program, and that gives you optimal play. Okay, making it fast. We'll skip that slide. Well, actually, this is interesting. If you can't list the entire search space because the kid has made your problem too big, you take 20 possible plays, just start guessing them randomly, and then you evaluate out of those sample of possible plays. Say, I have 20 possibilities that I'm going to try. Out of millions, I'm going to explore those and see the information content of each, and when I've computed the information content, I'll choose the best of those. And it turns out that gives you very close to optimal play, but it's much, much, much faster because it doesn't search every possibility in the search space. I think there's a lot of statistical lessons here. There's lessons about using computers to solve problems. This one's particularly interesting because unlike other puzzles where you just compute a direct solution, this is more science-like. We're teaching kids generate probes that give you information. How does that relate to a science class? Like, if you're going to perform an experiment, provide an experiment that gives you some useful result. Devise a test to see if there's life on Mars. Useful result would be, hey, let's ask the Martians. Even if they say no, the answer is significant. Okay. So, basic framework takes 30 lines of code. 4 different strategies took another 30. It's easy to try out even more. The end result is not far from the theoretical optimum. I think that makes a great lesson for kids. How many people love it? All right. I have a theory. All real programmers who've been forced to solve more than 3 Sudoku problems get bored with solving Sudoku problems and want to write a program to do the same. It's not hard. We'll quickly go through the code for it. It's a simple constraint solver. It makes guesses and then it propagates out the effect of that guess, eliminating remaining possibilities and continuing down the search tree. I should take a brief aside and just say, lots of people have written Sudoku solvers. They're all boring. It's fun to write one, but it's boring to read other people's. Except for one. At OSCON, I had to go see a person do a 1-hour presentation on his Sudoku solver written in SQL. It's impressive. It can be done, and it was brilliant. Man who can solve Sudoku with SQL can do anything. Okay, so here's what Sudoku looks like. Who here is familiar with those puzzles? Great. We won't go into them in any depth. The interesting thing is the translation from what's on the right to what's on the left. Apologies, the photo image doesn't correspond to the letters here, but you get the gist. So there are empty spaces. You have to figure out what goes in there. Obviously, the permutation generator won't help here. Search space is rather large. Here's what a completed puzzle looks like. So the interesting part is using a constraint solver to pare down the possibilities. Code only takes 56 lines. It's easy. The interesting part of many AI problems is not the method that you use to solve them, but the choosing a representation. A simple representation I came up here is, let's define the problem as a string with spaces representing the unknowns. One of the problems with having a representation like this that's convenient for the computer is it's inconvenient for you to read, so the first thing you write is a show function that takes a string like that one and displays it like this. Not hard, just basic string formatting using a couple of joins and prints. Okay, determining the cells that are in contact with each other. If I had this to do over again, if I were teaching it to kids, I would not write this function this way. Instead, I would just make a dictionary and itemize it out. I'd put, this cell is friends with everything else in this grid of 9, and friends with everything else in the same row and everything else in the same column. Here I generated it programmatically, but the thing is, you could lose 1 or 2 sessions of your class with kids teaching them to write this function. It'd be better, but it's not the interesting part of the code. So give them a big dictionary that just shows how the cells link together, which cells are friends with each other, which ones are in opposition to where you can't repeat the same digit twice. Same digit can't go on the same corner square, same row, or same column. So I'd skip that part. Oh, by the way, the SQL guy skipped this part too and put it in a table. Gives you a hint of how he solved it. Write the solver. Wow, most of the code here is comments. Python's easy. Loop over all pending guesses. Put in a guess, find the friend cells, the ones that it's adjacent to, mark out the possibilities on those cells. Say, well, if I put a 3 here, I can't use a 3 anywhere else. And continue marking out, taking the consequences of your guess, percolating them through as far as possible. Then when you get stuck, loop back and try again, recurse down the tree. Not terribly exciting. Here's a slide describing the logic. Make an assumption. Go to all the friend cells, eliminate the possibilities made by that assumption. Oh, this is important. Always teach the kids at any given point, check to see if the puzzle is solved. An amazing number of programs won't terminate because they've already solved the puzzle, but continue searching. This is also a lesson for us adults. I've done that once or twice with my career. Okay, some cell goes down to one possibility. Hey, let's fill that in. I've eliminated all of the other possibilities down to one. If there's some cells unsolved, make another assumption. If an assumption turns out to be invalid, unmake that assumption, backtrack, start again. The interesting part of this code, about a dozen lines, can be covered in an hour-long class. Bayesian classifiers. Hot topic. Fun for kids. Good for statistics classes. The best Bayesian solver to play with for kids is to go pull out the Reverend file. Does anybody know the name Reverend Thomas? Where that comes from? Yeah. It's his name, Reverend Thomas Bayes. Okay, so the principle of a Bayesian classifier is that we take a corpus of data to compute conditional probabilities. Let's say that we are trying to determine, the hot topic of the day is separating spam from ham, good email from bad email. So you divide it into a corpus, a pile of bad email and a pile of good email. And you'd like to find characteristics that the presence of the word sell now, what probability is it that it's good email or bad mail? Some good email may have it in it, but it indicates a probability. if it has the word Viagra in it. For you, that might be ham. For other people, it might be spam. The interesting part for the Bayesian classifier is it takes many attributes and their probabilities, multiplies them all together, and comes up with a joint probability. The thing to teach the kids in the statistics class is that is mathematically improper. Bayes' theorem, one of the first things they learn, says you have to divide by the joint probability. So what is the joint probability that, given it has cell now and that it has Viagra in it, that it's actually a piece of ham? Problem is, joint probabilities are really hard to come by in empirical data. You have to have giant data sets. So this is not really a Bayesian classifier, it's a naive Bayesian classifier. Naive meaning that we ignore the joint probabilities. It's an interesting part of the history of artificial intelligence research that it was held up for years by trying to do things properly. In speech recognition, they tried to teach it to computers to listen the same way we listen to. Ultimately, they ended up just taking a set of words and doing a nearest match on the waveform, and that seemed to work pretty well. And instead of trying to do it right, the approximation worked better. Turns out naive Bayes is remarkably easy to implement, and in many situations gives you the right answers, ignoring the mathematically correct way of finding the joint probabilities. So AI researchers missed this for years. They tried to find the joint probabilities. They needed giant data sets. They needed many hours of training the computer. And it turns out the training can be done real quickly when you just ignore the joint probabilities. So, simple example. We have to determine which decade someone was born. The attributes are, we know the person's name is Gertrude. Well, we can look up probabilities that Gertrude was a more popular name in the 1940s and 30s than it is with all the Stephanies and Megans and Heathers and Ashleys and Madisons that we have now. Turns out our favorite dance is the foxtrot. Now, there are some people on foxtrot. It's coming back in some of the ballroom dance classes, but we have some probabilities for the age group. You put all the attributes together, and we don't know the joint probabilities here because we know very little about the number of people named Gertrude who also know foxtrot. But if we ignore the joint probabilities, we can multiply those together and get a pretty good estimate of Trudy, who dances the foxtrot and lives in the burbs and drives a Buick Regal, is probably 55, 60 years old. Tricks of the trade. We've thrown away exact computation, gotten a best approximation. It works darn well. Coding in Python, really, really easy. The hard part of every Bayesian classifier I've ever seen is the parsing up of the words, the coming up with the attributes. So in the hot application of today, separating the spam from ham, if you look at spam Bayes, for instance, let me use the big diagram. Here is the amount of code to parse the email into attributes and interact with Microsoft Outlook and whatnot. The part that actually does the naive and Bayesian calculation is that big. It's tiny. It can be taught to kids in about 15 minutes. Here's a quick example of language classification. We train the guesser. It is French if it contains any of these words. It's German if it contains these. Spanish, these. English. Now we give it sentences like, they went to El Cantina. It grabbed the L and presumed that it's Spanish. It gives you an idea of how a Bayesian classifier thinks, if you call it thinking. They were flying planes. It guesses that it's English. Turns out a remarkably simple amount of training can make a pretty darn good classifier, and I think this is useful in lots of web apps. You can tell from the nature of a query that is given to you or a user email probably what language they were speaking. Easy stuff, very useful, and the effects of which remarkably resemble artificial intelligence, meaning the computer read my email and it could tell which language I was speaking. It's awfully smart. Hot topic, spam from ham. Go check out the Reverend Thomas Bayes site. It is a very clean, beautiful piece of Python code. My generic puzzle solving framework. This thing is awesome. It cannot be presented in 1 minute, which is how much I have. So you can Google for puzzle and Hettinger, and you will find it. You can download it from my website. You can look at Wikipedia for depth first search, or you can come over to the open discussion rooms later and we will go over it. In my 30 seconds or so, what does a generic puzzle look like? A generic puzzle has an initial position, a rule for generating all possible legal moves, and a test to see whether the end state is a goal. Optionally, you can add in a way to print it out. The interesting part of these problems, once again, is to figure out how to represent the problem. The puzzle solver simply takes the initial position, finds all the possibilities, starts to work its way out, either breadth first or depth first, until it finds the solution. The astonishing part for kids is how many puzzles it can solve. The golf tee puzzle. Let's watch it go. Here's how you do the little jumping of the marbles, and you try and get down to a state where you only have one marble left. The framework finds this rather quickly. The jug filling problem. How do you pour one jug into another to leave exactly 4 liters in the largest jug? This is an example of the code for the jug fill problem. It inherits from the puzzle solving framework. It has an initial position, the capacity of each jug, and an iterator to generate all possibilities. And the goal state is 0, 4, 4 as defined in a problem. This is a direct translation of those words. These words are this description. And since you've inherited from puzzle, all you have to do is say run, and it produces the result. Pap, 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 pap. Easy peasy. The marble jumping puzzle. Here's the solution to it, finds it in moments. I'll tell you about how the puzzle works later. Sliding block puzzle. I love this puzzle. It's my grandfather's house. It was a mother to solve. It was the only puzzle that I couldn't solve within minutes of getting it. This one took months. Oh, took my program seconds. You slide the big block, the blocks around until this block is down here. Seems easy. There's a fairly long sequence of moves. To solve the puzzle, I inherit from the framework to find initial position. I look at the goal state to see when the one block is in the lower right-hand corner. A representation so I can print it out in a pretty way. And define the block moves. And an iterator for generating the next possible move. This one's a little bit tedious to code, but it's fun, and it only takes 36 lines and knocks out the puzzle in seconds. Questions, suggestions, comments, or complaints? I have time for one question. Did you guys love it? You would make me happy if you would take one of these and show it to some child in junior high or high school and hook them on programming for life. Any questions? Thank you very much. We will. I'll be in the other room, in the open rooms, to discuss the details of any of the puzzles. Thank you very much for coming.
Hey, thank you, Raymond.